Alright guys, in this section we're going to be discussing derivatives of inverse functions. And we're going to come up with a formula that describes those derivatives. So here we have a couple of theorems. First one talks about continuity and differentiability of inverse functions. It's pretty straightforward. So we have if a function is continuous in its domain, then the inverse function is continuous on this domain as well. Also, if the function is differentiable on an interval containing some point c, and the derivative of that c is not equal to 0, then the inverse function is differentiable at f of c. Then we have our main definition here for our theorem for the derivative of the inverse function, and this is what we want to prove. Proof is pretty straightforward, guys. It comes from your knowledge of composition of functions. So using the notation that we have in the theorem, let's assume f and g are inverses of each other, right? G is the inverse of f, and vice versa, f is the inverse of g. So we have that if g is the inverse of f, if you recall, if we had two functions and they're inverses of each other, if we compose one with the other, we should get the input back. So we have that since g is the inverse function of f composed with g, in other words, f of g of x should be equal to x. If we take the derivative on both sides here, since we have a composition of functions on the left, we're going to use chain rule here. We take the derivative of f with respect of x, and then chain rule says you're going to multiply by the derivative of the inner function, which in this case is g. So the derivative of g with respect of x. All of this equal to the derivative of x with respect of x, which we know is going to be 1. Okay, so here I'm going to write everything the same on the left, and on the right, dx is just 1. Derivative of x with respect of x is just 1. So rearranging this equation, remember g is the inverse of f, right? That's our assumption. I'm going to solve for the derivative of g of x. So dividing both sides by the derivative of f of g of x, we get that the derivative of g of x is equal to 1 over the derivative of f of g of x. And that's exactly what we had in the theorem above. Now, using Newton's notation, we have the same thing. G prime of x is equal to 1 over f prime of g of x. And of course, don't forget that the denominator can't be 0, otherwise it'll be undefined. Okay, so here's an example. We have our function sine x. The inverse we already know is arcsine, or sine inverse of x. So our f is sine x, g is arcsine. And we're going to find what the derivative or arcsine is. We're going to use the theorem, right, that we just derived, that we proved here. And if we use here our expression from above here, we get that derivative of arcsine x is equal to 1 over the derivative of f, which is cosine of g of x, which is arcsine of x. So we plugged it in there. Now, to get an algebraic expression, we'll need to rewrite cosine of arcsine of x in terms of x. And this was a skill that you learned in your trigonometry class. So here it is. I'm going to let arcsine of x be theta. By definition of the inverse sine, we get the sine theta is equal to x over 1 using a right triangle trigonometry. We can find that third side there with the Pythagorean theorem. Sine is opposite of a hypotenuse. I can find the adjacent. Since the denominator is cosine of that theta, I can find cosine of theta from my triangle here. It'll be adjacent of a hypotenuse, which is just square root of 1 minus x squared all over 1. Now remember that our derivative of arcsine is 1 over all that. So then our final expression would be 1 over the square root of 1 minus x squared. And there it is. We have the derivative of arcsine, sine inverse. So this is our new rule to add to our bank of derivatives. Now in the same way, you can find the derivatives for all the other inverse trigonometric functions. For the sake of time, we're not going to do all of them here or derive all of them, but you can do those on your own and using the same technique that we used here. So now let's describe the general rule here for the derivative of sine inverse. And when I said general rule, remember the chain rule is going to generalize all this. Instead of having x, let's pretend x is just a function of x, right? And we have a rule now for derivative of arc sine, which is 1 over the square root of 1 minus, not x anymore, but it'll be the function of x, in this case f of x here in our generalization. And don't forget to square it. So it'll be square root of 1 minus f of x, all of it squared, f of x squared. And because f of x is a function of x, chain rule tells us to multiply by the derivative of f with respect of x. And there we have it. Just like arc sine, we can generalize all the other the derivatives of inverse trig functions. Here they are. This is the summary for, and they're using u here as a function of x. I used f, but it's the same idea. You have the derivative of all the inverse trigonometric functions here. Notice here, all of these were derived the same way we did for arc sine. So you can do that as extra practice. And remember that u prime there is that chain rule that we're applying. Now remember, we're not doing just x anymore. We're doing a composition of functions, so we're generalizing all these rules, the derivatives of the inverse trigonometric functions, with a function of x so that we always think of chain rule. All right, so let's look at a quick example here to show how the rule works. We have y equals arctangent of e to the x. Want to find the derivative of y. It's the derivative of arctangent. So you look at your rules here. Arctangent is going to be 1 over 1 plus the input or the argument of arctangent square, which in this case is e to the x, all of that square. And chain rule says you multiply by the derivative of e to the x, which happens to be e to the x. So that's that u prime there that you see on top of all those derivatives. And then, of course, cleaning it up a little bit, we get e to the x over 1 plus e to the 2x. Here's another example. We have y equals arc sine 3x over x. We want to find the derivative of y, or in other words, the derivative of arc sine 3x over x. And since we have a quotient, we have to apply quotient rule here. If you recall your quotient rule, you're going to take the derivative of the numerator, which is arc sine of 3x, times the denominator, which is just x, minus the numerator, arc sine of 3x, times the derivative of the denominator. And that arc sine should have been 3x, guys. There's a small typo there. And then we have the derivative of arc sine of 3x, again, using our rules, would be equal to 1 over the square root of 1 minus 3x all of it squared. And then chain rule, multiply times 3, which goes on top there, right? Now remember, we were multiplying times x there. So we had an x right there, 3x on top. All of this is divided by x squared. Now remember, guys, this little typo here, that should have been arc sine of 3x, not x. Now, at this point, we're done with the derivative. We just want to simplify the expression a little bit so that we don't have a fraction over a fraction. So the rest is just algebra here. Okay, so here we have another example. Y equals x times arctangent of 2x minus 1/4 natural log of 1 plus 4x squared. We're going to find the derivative, and notice how we're using several rules from before together with our new rules, the derivatives of the inverse trig functions. So on the first term, we're going to use product rule, right? X is multiplying arctangent of 2x. So derivative of x is 1 times arctangent of 2x plus x times the derivative of arctangent of 2x. And using the rule, I get 2 over 1 plus 2x squared. right? And that includes chain rule and everything. Now, minus 1/4 derivative of natural log is 1 over the input of natural log, which is 1 plus 4x squared, and then chain rule on that inner function will give you 8x on top there. All right, so then simplifying it a little bit. Again, at this point, we've computed all the derivatives. We just need to clean this up a little bit. Get arctangent of 2x plus 2x over 1 plus 4x squared. Right? 2x all over the square gives you 4x squared. Now on the last term, the 8 and the 4 turns into a 2 there, and we have minus 2x all over 1 plus 4x squared. And notice how we end up with two terms that are going to cancel out. One came from the product rule of the first term, the other one came from the derivative of the natural log, but we end up with the same expression here. Since one is positive and the other one is negative, they cancel each other out, and we have our final answer is arctangent of 2x. The derivative of this whole function on top was equal to arctangent of 2x.